Hey everybody, today we're going to be discussing the different ways that we can use buffers to work with acids and bases, and also what hydrolysis means. Hydro and lysis. So you have hydro is a root, and that's going to be meaning water, and lysis means to break down. So when you're thinking about what water is a combination of H2O. It has also H3O+, which is also known as hydronium, and it has hydroxide, or OH-. The equilibrium of these three species allow us to observe what we call pH, which in any kind of aqueous or water-based solution is going to be essentially the balance of positive and negative ions and then neutral molecules of water, and basically what abundance certain species are in that solution. So when you're looking at, let's say, a strong acid, you're going to have a large abundance of H+ ions, which are going to actually exist in solution as hydronium ions, H3O+, because the H+ ions will not exist solely on their own. They will always be stuck to something. Then you have hydroxide, which is the OH-, which means that it has lost its H+ and has taken on a charge of -1 as an anion. In order to figure out the balance of those ions in a practical mathematical way, we use pH. pH is the negative log of the H3O+ or hydronium concentration in any solution. And if you think about adding an acid to a solution, what's going to happen? You're going to be adding so much of those ions, those H3O+ ions, that on a logarithmic scale, your pH is going to be going down to anywhere as low as 0 in the case of a really concentrated strong acid, or more likely in the range of 0 to 7 for any number of weak acids. Then you can think about a base, which is going to be analogous to that, and you're going to have a base existing between the pHs of 7 and 14, where you're going to have a higher concentration of the hydroxide than you are of the hydronium. For now, we're just going to take a look at a basic pH meter, which is going to give us a way to sort of get a gauge on what the pH or the acidity or basicity of a solution is in any particular solution. So what we're going to start with is this pH meter, and it has a storage solution on its probe, and the probe is basically just a porous glass ball that can allow permeation of water in and out. And this electrode can basically measure the conductivity of that liquid. And the way that it interacts with the probe will give us a reading, which is what we know as pH. And it's calculated by this instrument. So I'm just going to turn it on. Usually, anytime you work with one of these pH meters, you're always going to be looking at first whether or not it needs to be calibrated. So you'll use what we call a buffer, which I'll explain a little bit more later, to pick a particular pH and create a solution at that pH, which can be resisting any changes in concentration of hydronium or hydroxide, any changes in pH. That will allow us to look at exactly what the pH of a measured solution versus our unknown solutions will be. So once you remove the solution that you're storing the probe in, it's not the kind of solution that you'd want to have in all of your other solutions that you'll be measuring. And so what you'll do is you're going to rinse off your probe. And this particular instrument has a setting which allows us to see whether or not it has already been calibrated, which in this case it has, and it has a little smiley face which informs us that it is not in need of a new calibration. So we're going to just get going. And once we have our probe washed off, which you can, if you look here closely, you'll just see basically a tube which is full of a potassium chloride solution and a silver chloride solution inside of that, or a silver wire. We're going to take one of these test tubes and we're going to fill it with just DI water from the bench. just to give a demonstration of how this thing works. And we're going to move this out of the way. Dip this pH probe into the water. And we'll hit read. So what it's going to do is it's going to allow the probe to take a reading, and once it finds an actual average reading that it gets from the solution that's been placed in, it'll blink and tell me that it's ready to go and that it has a reading. It also gives me the temperature. In this case, the first temperature is 19.1 degrees Celsius as read by the tip of this probe. Currently, it's sort of moving around a few different pHs, sort of reaching an equilibrium here. .57. Finally, it took a little while to equilibrate because this is an equilibrium-based process. You're going to always have ions going from one side of the equation to the other, going from hydroxide to water to hydronium. And once the probe finds a steady reading, which in this case is 7.57, it will stop at that reading and stop recording. So this is for standard DI water from the tap. The next thing we're going to do is we're going to actually look at the pH of some DI water that was pre-boiled. So pre-boiling DI water is useful because there is a small concentration of CO2 that will always be dissolved in any kind of water. The way that we think about the ocean becoming acidified based on the CO2 concentration in the air is the same way that carbonic acid forms in any kind of water that is left out to sit, because CO2 has some solubility in all water. Depending on the temperature, it has some level of concentration that's going to vary. Let's say if you just put it on a hot plate and let it cook for about half an hour, you're going to remove a lot of the CO2. But once it cools down, some of it returns. So you always do your best to remove as much as possible for any kind of pH readings. So I'm just going to fill this up about most of the way. A little bit back. This one was a little too full before. And so for this sample, we're just going to place the probe inside again and allow it to record the new pH for the boiled water, which is going to be a slightly higher temperature. So the pH of the boiled solution turns out to be 6.94 at 32.4 degrees Celsius. So that was a first little trial just to get used to this pH meter. And this water is going to be really sensitive to pH change, mostly because it is completely unbuffered. There are no ions in there to prevent any kind of H plus from being preserved by some other salt ion, or hydroxide being preserved by some other kind of ion in solution that would be, let's say, a cation. So one thing that we notice here is that for whatever reason, the unboiled water, which we got from the wash bottle, is actually going to have a higher pH, or is going to be less acidic than the pH of the boiled water. A couple reasons for this, potentially. So the pH of the boiled water and the unboiled water were at different temperatures. That's going to already be corrected by the pH meter. This is a pretty standard, not really high-end pH meter as well, so that's not going to really make really that much of a helpful difference here either. It's going to take a little bit longer to stabilize and pick a pH, and also the temperature correction is going to be good. It's not going to be as great as it could be. So Then you're going to also look at the amount of CO2 in the atmosphere above these two samples. So if you think about this sample, it's sealed away in this bottle and it's less likely to have extra CO2 mingling with the surface, allowing it to probably stay at a higher pH closer to neutral than allowing CO2 to just directly dissolve into it as it cooled. When it came out of the DI water generator that we have here on campus, it probably went directly into this bottle without a whole lot of access to the air around us, which has about 420 ppm of CO2 at any given time, going up as we all know. Then you have this water, which is a little warmer and was boiled, but had full access to all the CO2 in the atmosphere and was allowed to equilibrate as it cooled down. As it cools, even though you may have boiled out the CO2, some of the CO2 may be returning, and so it's probably better to, let's say, backfill this with inert gas, which would prevent any kind of CO2 from dissolving as the liquid cooled and increased in solubility with gases. Either way, our first two data points will be shown later in the video, but keep that in mind. These two pHs are our first attempt at using this probe. So if we take buffers, what is a buffer good at? A buffer is good at resisting changes in pH. Instead of this solution or this solution, which are just pure water without any added ions, they're going to be more resistant to changes in pH because they have a salt that is allowing a particular equilibrium to sort of maintain one particular pH. And that particular pH is going to depend on what kind of salt you use. I have labeled some test tubes. We're going to be working with acetic acid, or HAC. We will be working with sodium acetate, or NaAC. We're going to have Na2CO3, or sodium carbonate. And we're also going to be working with ammonium chloride. So you have this acetic acid solution, and it's already been allowed to equilibrate. You have some concentration of hydronium, which is H3O+. You have some concentration of acetate. But mostly, if you start with the pure acetic acid, because it's a weak acid, you're going to have in concentration mostly the acetic acid left over. It's going to leave us at some particular pH, which is going to be representative of the relative concentration of that conjugate base and the actual hydronium ion. Remember, pH is always calculated by the concentration of the hydronium ion. And so you're always just going to have some particular amount of hydronium in any aqueous solution. So let's just throw this. This was already in DI water. Give it a little rinse anyways though, just to make sure that you're not going to cross-contaminate any of these solutions. You always want to rinse between each of the readings. And I'm going to dip it into the tube and hit read. So we're sitting around 2.87 at 20.6 degrees Celsius, and we're waiting for this pH to steady, and it just did at that 2.87, so I'm going to record that. And if I add a little bit of acid or base, you can expect that it's going to either, if you add acid, go down, or the pH will increase as you add base. If the pH increases, you're basically saying that the concentration of the hydronium ion is decreasing. But the nice thing about a buffer is that it will resist any change in this pH because you're going to have some concentration of that acid, HAC, or the acetic acid, which will get basically deprotonated first before the water is deprotonated by that base. So next we're going to set up the sodium acetate, and this is almost exactly the same as the acetic acid, except it doesn't have that H+ to begin with. If it goes into solution and reaches equilibrium, it's going to reach a similar equilibrium that's related to the pKa of acetic acid, but in order to reach equilibrium, it's going to have to take some H+ from the hydronium that's in solution already, which means that you're going to have a pH that's going to be quite a bit higher. because it's not being supplied at all by the acid that we have in this first sample. All right, as before, you always want to rinse off your pH probe before you move it into the next solution. Nice thing about these is they're pretty quick once you get them going. Just gotta make sure that your probe is ready. So here we're just gonna give it a rinse with the DI water into just a waste beaker. Obviously it should be labeled, I know. And I'm gonna put that directly into the sodium acetate. So try to make a guess before we get going of whether or not the pH is gonna be higher or lower than the original solution, which is gonna be the acetic acid. And this is just a conjugate base with sodium replacing that H+ ion. So see what you think. All right, so we have a pH of 7.20. It just finally reached equilibrium. And this is for the sodium acetate solution, and it is at 19.8 degrees Celsius. So glad to know that all the solutions here are pretty close to what you'd expect room temperature to be. So next we're gonna do some sodium carbonate. Sodium carbonate is similar to a buffer that you already have in your blood. A lot of your blood is buffered by carbonates. And all we're gonna do is, as usual, just place the probe inside of the tube and hit the go button. And then we wait. I decided to fill these ahead of time just to save us a little bit of dead air. All right, so for the sodium carbonate, which just steadied out, it's gonna give us a pH reading of 11.53, quite basic indeed. And that solution is at 19.5 degrees Celsius. All right, next we're gonna have a rinse here and get started on the ammonium chloride, and then we'll get started on making our own buffer.
What's it currently at?
6.48.
I'd say call it 6.48.
Just give it like 10 more seconds. Yep. Got a good feeling about it. All right, so after waiting a little longer than expected, we finally got to the equilibrium pH, which was read at 6.47. And it is at 19.6 degrees Celsius, and that is going to be our reading. So now we're going to prepare a buffer, an acetic acid buffer made out of acetic acid and sodium acetate. We're going to combine those two in a particular proportion, and that's going to give us some desired pH, which we could, using the math, calculate to any pH that we are interested in, depending on what the pKa of that particular species is. For acetic acid, the pKa is 4.76, and we are basically going to be able to use that to understand the balance in the relationship of concentrations between the acetic acid, which is neutral, and the acetate anion, which is the conjugate base and is negatively charged. Next is we're going to take all of this and we're going to add it to the flask. So this sodium acetate, all 4 grams, 4.020 grams to be exact, is going to go into this beaker. That's going to be pure conjugate base, balanced with a sodium plus ion, which is not going to contribute any extra acidity. Next, you're going to take a little bit of the 3 molar acetic acid that we have available, and you're going to measure out about 10 milliliters of that. So because you have 10 milliliters, you're going to be delivering some number of moles to this solution, and you should calculate that on your own. So here we have 10 milliliters of our acetic acid, 3 molar, and we're going to add that directly to the solution. I'm going to give it a little rinse too, just to make sure I get it all. So the overall volume of this solution that we're interested in achieving is 100 milliliters, and it smells just like vinegar, which is what acetic acid is anyways. A little bit less than 90. Perfect. And now we want to dissolve this solution, so I'm going to give it a little bit of a mix. Sometimes the crystals won't necessarily dissolve right away. We're just interested in a pH reading for the solution, and so we just want to have everything in solution. Doesn't appear to be any more particles of sodium acetate in there. So what we're going to do next is we're going to grab our pH probe, and we're going to give it a rinse as always. And once you give it a rinse, we're going to throw this sucker right into the buffer that we just prepared. Make sure that the tip of the pH probe is fully submerged, otherwise it won't work very well. Won't really work at all, to be honest. And very quickly, the pH stabilized at 4.70. So the initial pH of this buffer was 4.70 at 19.7 degrees Celsius, really close to 20 degrees Celsius. And the nice thing about this is that's pretty much what you would hope or expect, to have almost exactly the same concentrations of the conjugate base and the acid, because the pKa is extremely close to the pH. Taking this buffer, we're going to split it up and add a little bit of acid and a little bit of base to each of the different portions. So it's 4.69, which is extremely close to what it was before, 4.70. And I suspect that the other solution, which was prepared the same way, will be virtually the same. I'm actually going to put these into slightly larger containers, as it would be more responsible of me to do. This might be a little different than the actual procedure, but we're just trying to show you here that this can resist a change in pH, which was just measured at 4.69. Five milliliters of this acid. Now I'm going to add this directly to the acid and just give it a little stir. And then we're going to measure the pH. So our new pH of the acid is going to be, so after 5 milliliters of 1.0 molar HCl, that came out to 3.93. And the total volume of that solution will be 55 milliliters total. And it will have a temperature of 20.1 degrees Celsius. So we got this larger beaker, it's 150 milliliters, won't make too much of a difference. I'll transfer this buffer into this beaker, and we're going to look at some 1 molar sodium hydroxide in this case. So I'm going to give this a rinse. So I want to neutralize the base before you even use it. I want to avoid it at least. And we're going to add 5 milliliters of the same concentration of the strong base, 1 molar, to the same buffer, prepared the same way. Remember, this would have the same starting pH as before, so this is going to be a starting pH of 4.69, and it had a starting temperature of 19.9. Not that that matters too much since we have ATC, but worth noting. Give your probe a rinse, and we'll mix here, and we'll let that get going. So already we have a new pH of 5.67 at 20.8 degrees Celsius. And remember, this will have a total volume of 55 milliliters. So here, we're just going to see DI water. And we already recorded the DI water pH earlier, so we don't need to do that again as the initial pH. The initial pH, if you recall, of the unboiled water is 7.57 at 19.8 degrees Celsius. So then we're going to look at this water, and we're going to add 1 molar hydrochloric acid. We're going to add 5 milliliters of it. That's a little bit over 5, that's fine. Comparably small amount of solution going in. We'll see what change of the pH we observe where you have an unbuffered solution. So already we're working at an extremely low pH where it's beginning to equilibrate. We're looking at a pH of about 1.25. And that is considerably lower than what we measured before for adding 1 molar of hydrochloric acid, or 1 molar hydrochloric acid to the buffer, which gave us an equilibrium of 3.93 for our pH. Still going down too, so we'll see. All right, so we have our equilibrium, and it is giving us a pH at 1.20. So 1.20 at 20.6 degrees Celsius. So that is a significantly lower number. It's about 2.73 lower than the other pH in the buffered system. And that huge change in pH can be attributed to none of the acetate ions there to pick up some of that H+, which was added by the hydrochloric acid. Essentially, those acetate ions can't sacrifice themselves to prevent any increase in H3O+ concentration, and that's what you're seeing here. The same thing would be observed if you added base, or sodium hydroxide in this case, a strong base, to a pure solution of DIO water. And for the sake of wrapping this up, I'm not going to do that today, but you can expect that you'd have an appreciably large amount of sodium hydroxide